Okay, this is static, and we are solving the problem 321 from the book from Ebeler. So there is a way to solve it that is described in the solution, but I will just show you another way that is a little bit faster at some point. You will see the beginning in the same. Okay, so first analyze the situation. Okay, so we have a force P that we know. What is in blue is what we know. Okay, that's the force P. There's a tension in the rope on the particle A, and there's a force of the spring. I will call the force of the spring Fs, and T is the tension in the rope. Okay, so when we need to solve that, we need to have some information about geometry. Okay, let's say that the axis from there, we have an angle theta that is given that is 60 degrees. So it means that this angle there is also 60 degrees. Okay, so we are able to split the vector t, the vector of the tension, on an horizontal and vertical line. Okay, for the force of the spring, we don't have the direction, so let's call this angle alpha, and we will need to find it. And that's the first step. So we need to, not necessarily the first step, but one of the unknown. So we need to find alpha. Okay. Also something, the question asks what is the entrance length of the spring AC. So the entrance length, we know that the force of the spring is equal to K, and K is given, sorry, I didn't write it, but it's 50 pound per feet time L minus L0. What is unknown in this equation? The force of the spring that we will solve when we will find, after we found alpha. K is given, L, we don't know L, and we don't know L0, and the L0 is our final step. So we need to find L, so I mean, let's draw purple. We need also to find L, this L there, this distance L. That's the stretch length in purple of the spring. So we need also to find L, and after that we will find the force of the spring to finally find L0. Okay, so that's all the step. What can we do first? Okay, I think, so it's a triangle. Let me draw it in green, this triangle there. It's a triangle, and we know one angle, theta, and we know two sides. We know that the rope is 2 feet long, and we know that this length is 4 feet. Okay, so what we can use the cosine law. Okay, so we will use the cosine law in the green triangle. So, I'm sorry, it's July 4th, so you can hear some fireworks, and that's evening. Yeah, I record my videos mostly evenings, so I'm sorry for the fireworks that you can hear. Okay, cosine law. Let's do the cosine law. What we need to find is L. So L square, it's equal to 4 square, this distance square, plus this one, 2 square, minus 2 times both side, time cosine of the opposite angle of L, that is 60 degrees. So L, it's equal to the square root of, we have 16 plus 4 minus 16 cosine 60, and cosine 60 is 1/2. So it's L 20 minus 8, square root of 12. That you can rewrite square root of 4 times 3. So it's equal to 2 square root of 3. Okay. I like to keep it this way. So L is equal to 2 square root of 3, and it's feet. So that's for L. Okay, so now we know L. So again, in these green triangles, now we know L. So it's 2 square root of 3. We need to find, we are solving for geometry right now. So let's find the angle alpha there. We cannot find the alpha inside the green triangles, but we can find this angle there. Okay, let me call it beta. This blue angle there. How do we find beta? So we need to find beta. We have the opposite side, that is 4 feet, and we also now have an information between theta and the opposite side of theta, that is L, that we find 2 square roots of 3. So we can use the other law in a triangle, in any triangle, that is a sine law. Okay? So sine law will say that 4, let's write it the other opposite direction, sine of beta divided by 4, it's equal to sine of 60 degrees divided by 2 square roots of 3. So we have sine of beta, it's equal to 4 divided by 2 square roots of 3 sine 60. And sine 60, no, it's not sine 60. How much is sine 60? Sine 60, sine 60 is square roots of 3 divided by 2, right? So sine beta, it's equal to 2 times square roots of 3 times square roots of 3 and divide by 2. So it's equal to 1. What did I make it there? Let me check. Yes, so yeah, I think that's correct. But beta is not 0, so no, that's not possible. Where is my mistake? Can you see it? You know what? There's no mistake. So sine beta equal 1, so it means that beta is equal to the inverse sine of 1. So we are there, it's 1. It means that beta equals 90 degrees. Here we go, we have beta, 90 degrees. There's no mistake. That was just 90 degrees. So now alpha. Okay. For alpha, we have 60 degrees, we have 90 degrees, so that's a right triangle. So alpha is 30 degrees, right? 60 plus 90 plus 30, 180 degrees. So here we go. We have the geometry. So we found L. We're good with that. We find L. We find alpha. Okay, let me write alpha. And so alpha is equal to 30 degrees. We find alpha and we found L. Okay, now let's go with the Freebody diagrams, and that's where I will do something different than in the solution of your book. So you have the point A, that the particle, we have the force P going down, and P is equal to 80 pounds. Okay, we have the force F, the force Fs, the force of the spring, and T, and we know angles. Let me do it a little bit better. T, and we can draw all the angles we have. We have 30 degrees, we have 60 degrees, but most important, we have a 90 degree there. So now, what do you think? What can we do? We need to solve for the force of the spring and the tension. Oh, for the force of the spring. Do we need to solve for the tensions? If we split on x and y, yes, we need to use cosine and sine on both, and we need to solve a system of 2 equations with 2 unknown. But if we don't use this x and y, but we use, sorry, I remove this one. We use this x. Oh, I'm too close. This and this y. And we can because there's a 90 degrees angle between both of them. Okay, so what does that mean? How much do we have with P? So we have 30 degrees there. So that's a 60 degree there. Okay, so if we use this x and we write sum of the forces on x, it's equal to 0. We don't have the force T, the tension T, because the tension T is perpendicular to x. Okay, x. So what do we have? We have the force of the spring on x and minus P cosine 60 degrees, it's equal to 0. So the force of the spring is equal to P, that is 90, times cosine 60 degrees, and cosine 60 degrees is 1/2. So the force of the spring is 40 pounds. So much faster, no? So much faster to solve for the 40 pound than to do a system of 2 equations and 2 unknowns. Okay, and one last step. The question asks the unstretched length. So we have the force of the spring that is equal to K times L minus L naught. So the force of the spring is 40, K is 50, L is 2 squares of 3 minus L naught. Okay, so 40 divided by 50 is equal to 2 squares of 3 minus L0. So finally, L0 is equal to 2 squares of 3 minus 4 divided by 5, L0, L naught, 2 squares of 3 minus 4 divided by 5, 2.66 feet, L naught. Does that make sense? Always check that makes sense. Also check your units. 2.66. So just to compare with 2 square root of 3, 2 square root of 3 is 3.46 feet. Okay, so I mean that this distance there in purple is 3.46, and this distance there, the minimum that is possible is 2. So your which color? It's too orange. That means that your spring is somewhere there, and your rope is there, and the rope is always 2 feet long, and this one is 2.66 feet when there's no force, no pulling force downward. That makes sense? Yes, because it's between 2 and 3.46. That is the maximum. So that makes sense. So we are happy with our answer, and we are happy to solve it faster. And that's it. Thank you for listening. See you in the next video. Bye-bye.